Okay, we are going to wrap up this lecture by talking about a few other features of vowels, which can give us a little bit of insight into perturbation theory as well. So there are some languages in the world which have a feature called advanced tongue root. This is found in a lot of West African languages. There are some analyses you can see in the phonological world primarily that talk about advanced tongue root is basically the corresponding feature for tense lax in a language like English. That's not a great way to think about it, so try not to do that. Instead, what's going on here is that you're basically making the same vowel in kind of a higher position of your vocal tract. And then in the back part of the pharyngeal region, you can either move your tongue root forward or push your tongue root back. And might be a bit hard to see that diacritic, but it's basically a vertical line with a horizontal line in the middle, either pointing to the left or pointing to the right. Yeah, that's going to be hard to see. I think we'll see some better examples on the next slide. If that little horizontal line is pointing to the left, that means it's advanced tongue root. If it's pointing to the right, that means it's not advanced tongue root, or what is sometimes called retracted tongue root. For our purposes, though, what we want to think about is what are the acoustic consequences of advancing the tongue root. And the way you can kind of think about it is that this will kind of create an anti-constriction, or sort of deconstrict the system at a particular spot. And where we are deconstricting the system is where we're advancing the tongue root. It's in the pharyngeal region, right? So what we should get here in terms of acoustic consequences are the opposite effects on our formant frequencies as what we would see for a pharyngeal constriction. So what are the effects of a pharyngeal constriction? Anybody remember? That's where we make a vowel like ah, right? Actually, I still have the board up. I didn't erase anything. The effect you should see is a screen arrow here pointing to the lower right corner of the space. You should get F1 to go up because you're close to an F1 node at the glottis, and you should get F2 to go down because there is a antinode at the pharynx for F2. So, I should have done that. If this is the effect we get with constricting at the pharynx, the effect we should get with deconstricting at the pharynx is to go in the opposite direction, which, by the way, is the same effect we would get for like a palatal constriction. F1 should go down, F2 should go up. It should sound more like an E, in other words. So an E with an advanced tongue root should be more E-like than an E that has a retracted tongue root. This E will be pushed in the direction of ah. Similarly, this oo will be pushed in the direction of ah. This oo will be pushed in the direction of E, more or less. And one way you can look at this, a tool that's really useful for it, is ultrasound. This is from a while ago when this technology was still relatively new in phonetics. This is from Brian Jick's lab at UBC on the coast. And this is a speaker of the language Kanande, which is spoken in Congo, which has this feature. And so you can see this is how ultrasound works. You place this transducer on the bottom of your neck while you're speaking, or basically on the underside of your jaw as you're speaking, and you can kind of tilt it back a little bit to kind of get a view of what the tongue root is doing back here. That's one of the reasons it's a really nice technology to use. It's also not invasive. You don't have to shoot x-rays at anybody to do this to get a sense of what's going on inside their mouths when they're speaking. Yeah, it's a little bit messy because you kind of have to put conductive gel on the transducer, but that's a minor inconvenience at best. Anyways, the representations you kind of get when you do this look like this, and this is oriented the other way, so this is the front of the speaker's face. This is the front of the speaker's face, and you can see the tongue root back here. This is easy to image on an ultrasound system. Again, with ultrasound, it can't go through the sound waves, can't kind of image through air. So where there's a gap between the top of your tongue and the air above it in your vocal tract, you get this white line, which more or less delimits where the tongue begins and ends. And you can see that the back of the tongue moves a little bit forward here. And it's further back here in the retracted case. So this is plus ATR, and this is minus ATR. It's a feature in the distinctive feature system. Okay, so here we go. These are some examples of plus and minus ATR vowels from the language Akan, which is spoken in Ghana. And you should be able to hear that the plus ATR vowels sound more high in front, and these should sound lower and backer, even though the top of the tongue is basically doing the same thing in both sets.
Si, se,
So this one should sound like an E,
si,
and this one sounds maybe like an A.
se,
We'll listen to the slightly lower vowels,
wabetu, se,
and all of a sudden this sounds more like a mid vowel.
se, wabetu,
So you can kind of see why people might confuse this with like a tense lax distinction. It kind of has similar acoustic effects on the vowels that it's produced with, but different things are happening articulatorily. Here are some back vowels with this distinction.
bu, bo,
And this one winds up sounding kind of like an open O.
bo, bu,
Similar for a slightly lower place of articulation.
ovia, ovia,
And this actually winds up sounding like a low backgrounded aw,
ovia, ovia,
because it's lower in general, right? Yeah, so we can look at the spectrograms for these guys.
si, se,
Here is F1 and F2 for E, kind of where we normally expect them to be.
si,
But if you have a retracted tongue root pronunciation or a minus ATR pronunciation, F1 should go up a little bit, F2 should go down a little bit because you're making a pharyngeal constriction, basically.
se,
So it sounds a little bit more like an A. Here's some plots I grabbed from the Source Sounds of the World's Languages book from a couple, like Akan, we've seen that language already, and this is from Doluwo, which is spoken in Kenya and Tanzania. I believe, if I'm not mistaken, Kofi Annan, he used to be the Secretary General of the United Nations, was a speaker of Akan from Ghana. And I believe as well, Doluwo is the tribal heritage of Barack Obama from Kenya. So this is, I don't know if this is language, if his father spoke this language or he just came from that region of the country, but either way, this is what their vowels look like. So you can see for a plus ATR vowel, it moves that vowel's formant frequencies in the direction of E in the high front part of the space, no matter where you are in the vocal tract in terms of the position of the top of your tongue. It's always going to move in this sort of upper left direction in the vowel space. Okay, that's what ATR does. Let's take a look at F3. We talked about this before in our previous lecture, that F3 comes into play when we're producing syllabically, or a vowel that's basically rhoticized in some form. Because for we're making pharyngeal, palatal, and labial constrictions, and each one of those constrictions comes at an antinode for F3. So if we produce them all together, then F3 should go down a lot when we produce it, because we're getting all three of these articulations to work together to the same acoustic effect. And this is what we see in English.
Bard.
This is F3 going down in the word bard.
Bard.
And it winds up sitting down right on top of F2 below 2000 hertz. So that's pretty effective, right? It's going from like 2500 to like less than 2000. That's how you lower F3, and it will help get it into a position where it's kind of easier to hear because the acoustic intensity is louder and our ears are more sensitive to this frequency range, a little bit more than to hear. Okay, I call that rhoticization. On this slide, I call it retroflexion, but if you curl your tongue tip back as you produce vowels, you get kind of an R flavoring to it, which is basically lowering F3. So this can be a feature which is contrastive in a language, and we observe it here in the vowels of Badaga, which is a language spoken in southern India. I think these samples are most effective kind of for the mid vowels. I'll play maybe not all of them, but here, when a vowel is rhoticized, you kind of have this curly Q, which looks a little bit like a cursive R, hanging on to the right-hand side of the vowel. And when it's not rhoticized, you just get the vowel as we normally transcribe it. So you can listen to these.
Be, 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 be.
And you can kind of hear that R flavoring on this one.
Be.
Be. We'll play some of these mid vowels.
No. Po.
that one's not the greatest example. This one, I think you can hear it better.
호구, 오게,
Orge.
호구, 오게.
Right. So if you hear that, that's what's going on. There's a bit of retroflexion on top of the vowel, and that would be how you transcribe it. And what you should see is that should lower F3. Here is the two front mid vowels.
배, 배,
One of which is produced with this rhoticization feature. So here's what F1, here's F2 around 2,000 hertz, and F3 is around 3,000 for this particular token.
배,
And then when we rhoticize it, we get F1, F2 is a little bit lower, and then F3 comes down and sits right down on top of the F2 for this one. So it's a little over 2,000 hertz.
배,
Kind of like what we saw for in Bard in American English. Okay, so let's think about this in terms of a different vowel articulation. So we talked not too long ago about U, why that was kind of a dispreferred vowel in the world's languages. We didn't consider what sort of effects the articulations you need for U would have on F3, but I'm plotting the F3 standing wave here on top of F1 and F2 kind of for the first time. And for U, we expect to get a labial constriction and a palatal constriction here. We know what that would do to F1 and F2. It would kind of work at cross purposes. We get lowering of both formants for F1 and F2. We get a rise in F2 for the palatal constriction, a lowering of F1. So the problem is that those would kind of work at cross purposes. But in general, we know that where we wind up in this vowel space, right? Kind of in a more high central position if we produce those two articulations. What happens to F3 though, based on perturbation theory? Looking at this diagram, if we constrict here and here, and the green wave is a standing wave for F3, what happens to F3? Any guesses? Hopefully this should be fairly intuitive by now, but you would expect F3 to go down, right? So these are antinodes for both the palatal and labial constrictions. We're here at an antinode around 10 centimeters here, and then here at an antinode at the front of the mouth for F3. So F3 should go down, and if we look at F3 in the production of this vowel, these are samples from French, we see it goes down a lot.
Li, lu.
So here's F1 for E, here's F2. F3 is way up here, maybe around 3,500 hertz, and this is what happens when we round our lips for it.
Lu.
We'd expect all the formants to go down somewhat. It's hard to see that for F1 because it's so low already. F2 goes down from about 2,400 to 2,000 or so, and then F3 comes down and sits right on top of it.
Lu.
So it looks like one gigantic formant compared to this F2 here. And that's,
Li,
lu. We don't consider F3 that often in terms of the distinctiveness of vowels, but this is something that could sort of contribute to the distinctiveness of U compared to other vowels, in that F3 is pretty low. And maybe one reason why there are a fair number of languages which have this vowel. I think we said there were 21 in the UPSID database in the previous set of lecture notes. So, it's possible, and we don't want to simplify our representations too much, but if the theory of adaptive dispersion holds true, then there must be some sort of distinctive value to this guy, otherwise we wouldn't produce it. And maybe we're finding it in F3. Okay, so lastly, I'll talk a little bit about over-rounded vowels. So typically, as you go from low to high in the vowel space and you're rounding, what will normally happen is you typically get more rounding on the higher vowels than the lower vowels. So there's more rounding on U than O, and there's more rounding on O than O. And this is maybe just basically a function of what your jaw is doing as you produce these. So if your mouth is a little bit more closed, like for the high vowels like U, it's easier to get the lips closer together for U than for lower vowels like O or O. So you're opening up your mouth a little bit more for these guys. You can't get the lips quite as close together, but you could if you really tried. So it's actually possible to have U-like rounding on lower vowels. And I've got some samples here from a language called Assamese, which I believe is also spoken in Bangladesh, sort of in South Asia as well. So I'll play, the crucial example is this one down here. So these are a couple low mid vowels.
เป็ดปด
These are a couple low vowels.
ปัด
And this is supposed to be a low back rounded vowel, but it's really rounded. So it has this kind of open O diacritic underneath it, which is going to basically be the lip rounding you expect for like ooh. And therefore this vowel is going to wind up being or sounding a bit higher because we're really kind of pushing those formants to a low position.
ปูดปดปูด
So it's kind of funny. This vowel, which is supposed to be lower than this one, sounds like it's this vowel, which is supposed to be higher in the vowel space than this one, winds up sounding like it's lower
ปดปูด
because of this effect of the over rounding of the lips. And this is what it looks like in spectrogram form.
ปัดปูด
This is basically the over rounding here, and this kind of winds up looking a lot like an ooh, as it were. So this is an ah with maybe a little bit of fronting, which is why you can kind of see some space in between the F1 and F2,
ปัด
which is why we're giving it this transcription, the script A.
ปัด
And then if we have the low back rounded, ah, but oh,
ปูดปูด
something like that, we get drastic lowering in both F1 and F2. So it's definitely acoustically in the high back region of the space. Articulatorily, there's a little bit more going on. That is not super common. Here's a contrast between the open O
ปด
and the low back one.
ปูด
And you can see that these formant frequencies are lower than they are for the open O.
ปด
So like I said, this one winds up sounding like it's higher
ปูด
than this one, even though in some technical sense it's not. These are not super common, but they're out there, and you might encounter them in your course project for this semester. But yeah, probably not. But if you do, let me know because I'll be interested to hear. And that's it for this lecture. Next time, as the next slide kind of implies, we're going to talk about theory number 2 for how we go from the articulation of vowels to their acoustics. So I will look forward to seeing you then. There will be more math involved, so just be ready.